So yesterday we talked about all those exponent rules. Today we're going to talk about radicals and then tie them into everything we know about exponents, so we can use all those rules even if we are working with radicals instead of exponents. So it's kind of a nice relationship because you can always write one as the other. So regardless of what we have to simplify, we can always use the most efficient way or simplest way to do it. So let's start with just some definitions as far as radicals go. So we'll start with the square root. That's the one we're most familiar with. So we say a number C, or let's just say it this way. C is a square root of A if when you square C, you get A. So a square root of A is any number that can be squared to get it. So for example, the square roots of 36 are what? So 6, yes. And what else can you square to get positive 36? Negative 6, good. Because if we take 6 to the second power, we get positive 36. And if we take negative 6 to the second power, we also get positive 36. Now, this is a little bit problematic because we just defined an operation that is not a function, right? Like, so any input I have is going to have two outputs because there's always a positive number you can square to get a positive and a negative number you can square to get a positive. So every positive real number has two square roots. And we don't really like that because it's not a function, right? We like working with functions because they're not ambiguous, right? If I give you 36, you give me one answer, the square root of 36. We don't want two answers. So we define a symbol to represent the positive square root to get around this problem of having two outputs for one input. So we say that we have two square roots for every positive real number. One of them is called the principal square root. Which is just another way of saying the positive square root. And we write this as that symbol. So people are, and I will be too, basically everybody is really lazy about this distinction between the principal square root and the square roots. So when we read that symbol, we typically just read it as the square root of A. What we really mean is the principal square root of A. So that symbol always represents a positive number. And that way we can define things like the square root function where we say f of x is radical x, and it only represents the positive square root, and so it only has one output for every input. So we're just using this symbol to narrow things down so that we can think of this as a function. And then if we wanted the negative square root, well, it's not very exciting. You just put a negative sign in front of the positive one. But again, this just allows us to have no ambiguity about what number we're expecting to get from these expressions when we simplify them. So it's a subtle difference between like saying what are the square roots of a number and what is radical 36. But if I gave you this problem, the answer would just be 6. It wouldn't be 6 and negative 6 because that symbol tells me I just want the positive one. It's pretty important that two of them exist, mostly for the purposes of solving equations, right? If I solve the equation x squared equals 36, I want every single number that can be squared to get 36. There's two of them, a positive one and a negative one, right? But if I am given x equals that, I'm just going to get a positive number. So we want to remember this bit about the two square roots so that we don't get in trouble when we start solving equations using square roots. However, I will, like everybody else in the world, be lazy and call that the square root of a rather than saying the principal square root of a every single time. That symbol will always represent a positive number no matter what. You can never write that radical symbol equals and then write a negative number on the right and have it be true because it's always going to represent a positive number. So let's do a couple of examples. So this is asking what is the principal square root of 25. We're just going to say what is the square root of 25, and we all just know it's the positive one. Yeah. What's the square root of 25? 5. Good. What about that? What's the square root of 5 squared? It's also 5, right? 5 squared is 25, so it's really the same exact problem as the one above it. What's the square root of negative 5 squared? So if I write, it's so tempting to say it's negative 5. But remember what we just said about this symbol? It always represents a positive. So it can't be equal to a negative. And if we, like, it's really tempting because we want to just, like, slash off that exponent and square root, right? Because they, like, undo each other. But if we look at it in terms of order of operations, if we do negative 5 squared, what do we get? 25, and the square root of 25 is 5, right? Like that one takes us right back up to the first one as well, which is kind of annoying because what we want is we would very much like to say that this is true. Whoa, I wrote negative 5 and I didn't erase it. I'm sorry. There we go. We would very much like to say that's true, but it's not because the example above, my x value is negative 5, right? I'm squaring negative 5. I don't get negative 5 as my answer, right? So saying that the square root of x squared is equal to x isn't totally valid because my x value could be negative, in which case I'm still going to get a positive output. So we have to make one little adjustment to our notation, which is that. So that tells me, so it's not that when I put negative 5 in, I'm going to get something totally crazy and wacky. I'm just going to get the positive version of it, right? So that absolute value tells me that no matter if x is positive or negative, if I take the square root of x squared, I'm always going to get the positive number that has the same magnitude as whatever x is. Now, we will start ignoring that pretty soon, but we'll talk about that in a minute. For our purposes, you want to make sure that you read the instructions in my math lab, especially tonight, the homework tonight in particular. There's a lot of different forms that things can be in, and so you really want to read the instructions and make sure that you understand what your answers should look like. So in the problem, they often say something like, assume that your variable can be any real number. That means it can be negative, so you need those absolute values. If it says assume your variable represents a positive real number, then you don't need the absolute value because the possibility that it's that x is negative doesn't exist. So we sort of use both for different reasons, but you just want it's really clear about which one it is. I think it says it in like every single problem. So just read those instructions really carefully so you don't end up getting frustrated over just notation, really. Okay, moving on to the cube root. Oh, I'm sorry. There's one more thing I forgot. Where do I want to do it? I'll do it right here. What do I know about the domain of a square root function?
Does it have to be greater than or equal to 0?
What does? Right, yeah, because it's not that x has to be greater than or equal to 0, right? Because it depends entirely on what else is going on in the expression. But it's called the radicand. The thing that's inside the radical symbol, we call the radicand, and that has to be greater than or equal to 0 because that's what we're taking the square root of, right? And we just said back here that positive real numbers have 2 square roots, but negative real numbers don't have any real square roots. Because remember, the definition says it's a square root of a if c squared is equal to a. So that means that the square root of -9 would be a real number that you square to get -9. But if we square a positive, we get a positive. And if we square a negative, we also get a positive. There's no number that I can multiply by itself to get a negative number. And so every negative number has no real square roots. And that's why the domain behaves the way it does, right? That's why we have to do that greater than or equal to 0, because whatever it is that's in that radical or under that radical has to be positive or 0. It can't be negative. So our radicand is greater than or equal to 0. And this isn't any different than what we've already done with domains. We're just doing a reminder because we're going to extend it to higher order radicals. So we just want to remember what we did. So let's find the domain. Of f of x equals the square root of, let's do 4 minus x. So the radicand in this case is 4 minus x. We want to take that whole thing. And we know it can't be negative, which means it either has to be 0 or it has to be positive. So it can be equal to 0, or it can be greater than 0. And these get a little tricky, so be sure that you actually do the solving of the inequality just so you end up with everything facing the right way. Because notice we have a negative x here. I think probably the easiest way to solve this, so you don't have to do the dividing by -1, is just to add x to both sides. So that just gives you 4 is greater than or equal to x. And then you don't run the risk of making sign errors with all those negatives and -1 and stuff like that. And then to write that in interval notation, I find it easiest to have my x on the left side. So you can just flip that whole thing over, including the inequality sign. So if 4 is greater than or equal to x, that's the same as saying that x is less than or equal to 4. So you can just flip the whole thing over. And that gives us negative infinity to positive 4, including positive 4. Again, same as what we did before, just a little refresher. Good? Okay, now let's talk about the cube root. So again, we're just going to start with the definition, and it turns out that the definition of the cube root is basically identical to the definition of the square root, except we're using an exponent of 3 instead of an exponent of 2. So the only difference between all these radicals we're going to talk about is like the exponent they correspond to. So we say that a number is a square root of another number if squaring the number gives you that number. A number is the cube root of A, so C is a cube root of A. If raising C to the third power gives you A. So we have all these different radicals, and the only difference between them is the exponent they correspond to. So for every exponent, there is a radical that undoes it. So a couple examples. What is the cube root of 8? It's 2, good. Because 2 to the third power is 8. What about the cube root of negative 8? Can I do that? Yeah, that one's negative 2. All the things that happen with the square root with respect to negative numbers happen because squaring any number gives you a positive, right? Like, so if I multiply 2 negatives, I get a positive. If I multiply 2 positives, I get a negative. So when I ask what number can be squared to get my radicand, it only works if my radicand is a positive. But the same isn't true of multiplying 3 factors that are negative, right? A negative times a negative times a negative is in fact a negative. So raising a positive number to the third power will give me a positive. Raising a negative number to the third power will give me a negative, which means there is a number that I can multiply 3 factors of to get negative 8. It's just negative 2. And all of this just stems from that idea that a negative times a negative is a positive, times a negative is a negative, times a negative is a positive, right? It flips back and forth depending on how many pairs of negative numbers you have. So that's the only thing we really rely on for all these rules about what you can and can't take the square root or the cube root or the nth root of. So every positive real number no, damn it, going on autopilot. Every real number, positive or negative, has 1 cube root. So the cube root of positive numbers is positive, the cube root of negative numbers is negative, and so we're not going to have anything with 2 answers. So what's the domain then of the cube root function? It's all real numbers, right? We just said in the sentence before that every real number has 1 cube root, which means I can take the cube root of any number and get a numerical value out, and that's what it means to be in the domain, that you can apply that operation to that number and get a numerical value as your output. So because we can do that with every single possible number, our domain is. I know this is kind of boring, you guys, I'm sorry. I have to write it all down so you have it. We'll get to do some problems here in a minute. Okay, we are now going to generalize everything we just said about the square root and the cube root in general, what I always remember is that even roots behave just like the square root and odd roots behave just like the cube root, because all the things we said about the positives and negatives have to do with the fact that squaring a negative gives you a positive. And it turns out that raising a negative to any even power does the same thing. And so that behavior is going to be identical. If the index, we call it, is even, it's going to behave like the square root. If it's odd, it's going to behave like the cube root. That doesn't mean that like all the outputs are the same or the graph will look exactly the same, but the behavior of it as far as domain, what things you can take the root of, etc., and the absolute value situation is going to apply to, or is going to be the same as the square root and the cube root. So let's talk the nth root. The nth root. So when we talk about the nth root, the only reason we use the letter n is so that we can talk about every single radical at the same time and not have to list every single possible number that we can put there. But it's not like you'll ever work with these as an nth root. You'll always have a number there when you're actually doing things with it. So like when we talked about the square root, n was 2 because it undid an exponent of 2. When we talked about the cube root, n was 3 because it undid an exponent of 3. So it's not that we're going to do this with variables in that spot. It's just that we want to be able to make generalizations about all of them. So we say C is an nth root of A if, and again, it's the same definition we used for the other two, if raising C to the nth power gives you A. So if n is even, then we find the domain by setting the radicand greater than or equal to 0. Again, all of the stuff I'm about to say about even roots just follows from exactly the same thing we did with the square root, right? The square root has index 2, and so it's got an even n. And then every positive has 2 square roots. Which means that, again, we have to make that definition of the radical symbol to represent the principal square root. So nth root. The principal nth root is written as the nth root of A. So n we call the index of the radical, corresponds to the exponent that it undoes, and we always put it in that little like nook in the radical symbol. So you want to be careful with this, like when you do like the cube root, you want to make sure you're writing it in that little area rather than like this, because that first one is the cube root and that second one is 3 times the square root. So because the square root is used most often, we don't actually write the 2. It has an index of 2, but we just don't write it on the square root. But all the other ones, we have to write it to indicate that operation, because each of these is a different operation. And then also the nth root of A to the n. If I have an even index, what should that be equal to? Yeah, the absolute value of A, good. So for the same reason we needed that absolute value for the square root, we need it for the nth root when n is even. And then if n is odd, what should my domain be? Mm-hmm. And we can say every positive number has, I should say nth. Has one nth root. And what's the nth root of a to the n going to be? Good. It's just a. We don't want the absolute value. I mean, it's not like the absolute value notation is optional here. Like, if we had the absolute value notation, we would be saying that the cube root or the fifth root or the seventh root of every number is a positive, which isn't true, right? When you take the cube root of a negative number, you get a negative out. So we don't want to throw that absolute value on there with odd roots, because it would make all our outputs positive, which isn't the case, right? So again, there's differences between the two, but if you kind of just rely on everything we know about the square root and then everything we know about the cube root, that kind of anchors you as far as how these guys behave. Let's simplify a few of them, just so we can see what they look like. So the fifth root of 32, my index is 5, which means I'm asking myself the question, what do you raise to the fifth power to get the number 32? Anybody know?
2.
Yeah, it's just 2. I always end up doing 2 because all the numbers get huge after that. So it's sort of redundant. How about the ninth root of x minus 1 to the ninth? So we see that my index and my exponent match, right? So my ninth root should undo an exponent of 9. So really the only thing we have to worry about is if we need absolute values or not. Very good. So we don't need the absolute value, or I shouldn't say we don't need it. We can't have the absolute value here because it's an odd index. So because my index is 9, if x minus 1 is positive, I'm going to get a positive. If x minus 1 is negative, I'm going to get a negative. So one nice thing about radicals is they behave really similarly to exponents in that if the only operation happening is multiplication or division, we can like pull them apart and put them back together all we want. So just like when we have a product in the parentheses, we can apply an exponent to both factors individually. The same is true with radicals. If I have a product inside the radical, I can take the fourth root of 81 and then the fourth root of x to the fourth separately. So what's the fourth root of 81? Do you guys know that one? Yeah, it's 3. And we're going to talk about this a bit more tomorrow, but if you don't know those, that's totally fine. You just use your calculator and do like the prime factorization, and then you can count up the factors and be like, oh, this is 2 to the fourth, so the fourth root of it's 2. So we'll see tomorrow. Prime factorization is going to be really helpful in simplifying the more complex ones. And then what's the fourth root of x to the fourth?
Would it be the absolute value of 3x or just x?
Great question. So it's both. So the absolute value of 3x is just the absolute value of 3 times the absolute value of x. And since 3 is positive and we know that, like, we don't have to worry about needing it to be the absolute value. And so we end up just writing this. Because the x is the only one that could be negative, 3 is going to be positive no matter what. But both are true. Any questions on the nth root? Does it make more sense, like, when you kind of see how we use it? Okay. So the last thing we're going to do today is talk about the direct relationship between exponents and radicals. So it turns out that we can go from exponents to radicals and radicals to exponents pretty seamlessly if we have like one little nice fact. So if I have the square root, we get to, now that we've talked about this all day, we can assume all variables represent non-negative numbers. So this assumption is pretty typical in most textbooks when we're first learning about working with these radicals and simplifying them and going back and forth between radicals and exponents. It's really tedious to try to figure out what to do with the absolute value in every step of everything. And so we like to just assume that all the numbers are positive, so we don't need absolute values, and we can focus just on all the simplifying we're going to do. And then later on, when it matters that you can have negatives, you'll reintroduce the absolute value. But it's nice to just focus on like one thing at a time and not try to juggle absolute value notation at the same time as trying to simplify these guys. So that's why we make that assumption. It's not because like we're saying negative numbers don't matter. We're just kind of narrowing the field a little bit so that we can make it a little simpler for ourselves. So we're going to assume that for the rest of the day. And so that means that the square root of x squared is just x. Because we decided x was positive, and so we don't have to worry about having to take the absolute value of it. And so what I want to do is I want to come up with some exponent that's going to achieve exactly the same result as taking the square root. So notice that we know that x is really just x to the first, right? So if I have x squared, I want to raise it to some exponent to get x to the first. What would that exponent have to be?
Negative?
So if I was adding the exponents, a negative would be really helpful, because when we do something like we could go like this, and we would get x to the first. But notice here we're raising an exponential expression to another exponent. What operation do we do there? So what would I have to multiply 2 by in order to get 1? 1/2, yep. Interesting fact, the reciprocal of a number times its reciprocal is always 1. So if you want to get a 1, you just have to multiply a number by its reciprocal. So like the reciprocal of 2 is 1/2, and so their product is going to give me 1. So what that tells me is that taking the square root of something is exactly the same operation as raising it to the 1/2 power. So we can generalize that and just say the square root of a is equal to a to the 1/2. This is really helpful because we had all those exponent rules yesterday that were super handy in simplifying things, but if we have a radical expression, we can't use them. However, if we can write it in exponential form, then we have all those rules to help us simplify things down further. And you'll really see the power of this when you take calculus, because to take the derivative of anything, it has to be in exponential notation. Like you can't take the derivative of a square root without writing it as an exponent. So that's one of the most useful things about this. But today we're just going to focus on kind of going back and forth just so we can use each of them interchangeably. So let's generalize this rule a little further. We don't want to just have to work with the square root, right? We want to be able to apply this to any radical. So the nth root of a to the m is equal to, I'm going to write it up here first. Well, just like raising x squared to the 1/2 power is the same as taking the square root, raising anything to the 1/nth power is the same as taking the nth root, right? Because that's the reciprocal of n. So if we multiplied those, we'd get that 1. But that's kind of ugly. And so I'm instead going to write it as a to the m over n. Right? So I just multiplied that m and the 1/n to get a single fraction so that I don't have to have two exponents. This rule right here is like the most important thing we've written down all day. So that's what helps you go back and forth between exponential notation and radical notation. And so it's probably really small on your piece of paper right now because it's not very big, but I would probably put lots of circles around it or stars or, you know, something, glitter. Because most of the problems people encounter on the homework tonight, like, can be solved by simply looking at this and doing what it tells you to do. It looks kind of funky, but let's work with it a little bit and see if we can wrap our head around it. So, I don't want red. So let's write with positive exponents, positive rational exponents. The word rational really just means fraction. So they're saying that instead of having radical form, we want to write this in exponential form. And this is another thing you want to look out for in the instructions, because there's no like more simplified version as far as if it's in radical form or exponential form. So you really just have to read what they tell you to do. So they'll say write with rational exponents, and that tells you you don't want any radicals in your answer. So if they say to write with exponents, no radicals at all. If they say to write it in radical form, then you want to write it in radical form, as that implies. So we're going to start with, let's do this one. We'll just do the 5th root of x. So what's that look like in exponential form? Yep, perfect. So the index is always the denominator of that fractional exponent. And we didn't have any other exponent here. I mean, we can think of that as a 1. But so we didn't have to do another number in the numerator. Whereas this guy is going to be what? X to the 3/4. So my exponent, my original exponent goes on top, and my index becomes my denominator. One of the really nice things about this is when we have something like this, we can write it in exponential form, which gives me x to what power? Yeah, so I have 4/8, but I can simplify that fraction now that it's a fraction and say this is the same as x to the 1/2. So even if I wanted my answer to be in radical notation, sometimes we work with the rational exponents to get us to a better radical, right? So this is just the square root of x. So like sometimes we start in radical notation and we want to end in radical notation, but using rational exponents to get there is super efficient and works out really nicely. And in practice, you guys will just use whatever works best in the situation you're in. Like I said, there's certain times you want radicals or certain times you want exponents. But for tonight, they're going to tell you what to do, so you can just practice using both. Let me do one more. We should do this one just so you see it. So what's that going to be equal to? That is very tempting.
Yeah.
But let's do one more step before we get to that, and then we'll see why we can't do that. So if we take that whole radicand, what were you going to say? Yeah, so the whole radicand, that radical symbol behaves like a grouping symbol, so it groups that x plus 2, which means when we take it out of the radical, we have to do that grouping with parentheses, and then to the 1/5. And then from here, it is very tempting to apply that exponent to both, right? But remember yesterday we said that if we have a product in the parentheses, we can apply it to each factor. But if it's a sum, we can't, because if we write that out as repeated multiplication, we still have multiplication and addition, and you have to distribute. So that's another little hiccup we have to just kind of remember, because it is really tempting to try to distribute over a sum or difference. But that's just as far as that's going to go. And last one, let's do 64 to the negative 2/3. So this one I'm just simplifying. Whenever I have a rational exponent, I always think about if a radical might be easier to use to simplify it than the exponent itself, just because we know a lot of radicals, like we know what like the square root of 64 is, or what have you. And so sometimes it's a little nicer to write it in a form that we recognize than to use those rational exponents. However, we cannot have a negative index on a radical. And so before you go from rational exponents to radical form, you always need to write it with positive exponents. So we're going to do that. Remember that negative exponent just says take the reciprocal of the whole entire thing. It's tempting because we have fractions in the exponents now to start flipping the exponents. We never take the reciprocal of the exponent itself. It's the whole entire expression. So this is going to be 1 over 64 to the positive 2/3. So the sign on the exponent changes. We take the reciprocal of the entire expression. And from there, I'm going to write this in exponential form, radical form. This is the third root, or the cube root, of 64 squared. One of the other nice things about the fact that we now know that radicals are really just exponents in disguise is that we can do them in any order. So just like x squared to the third is the same as x to the third squared, because you can multiply in any order you want, that exponent of 2 can either be on the inside and get done first, or it can be on the outside and get done second. And I personally don't even want to see what 64 squared is. It's quite large. So I'm going to write it like this. And I'm going to take the cube root first and then square the result, because then I get to work with nicer numbers. Does anybody know what the cube root of 64 is? It's 4, because 8 squared is 64. But so 4 times 4 is 16, times 4 again is 64. And again, it's okay if you don't know those off the top of your head. Just do the prime factorization of your radicand, and then you can see how many factors there are. So this is 1 over 4 squared, which is 1 over 16. And it got really simple really fast from there, right? So it's kind of nice to use radicals in that setting, just to because we're more comfortable taking the square root of things than raising things to like the 1/2 power. So I have homework for you guys.